operate a little differently than we normally do. Where we're going to start is, I noticed that there were some of the problems I gave you for homework were a little more difficult than I think. They were all doable, but I thought it would be use to go over some of them. I haven't looked at the homeworks to see who, how many people got these and how many people didn't, like my grader did. We're going to do that, and then how many people here have a TI kind of calculator with them, or have it on their computer? Okay, almost a lot of people. I have a few here that I can loan for today. I'm going to get a few more so that on the day of the exam, if people need them, they'll be able to borrow them for the exam. I don't think they'll be especially useful, but I'm always, students often prove me wrong. So, with that in mind, I guess, I don't know if this will work. Maybe it'll work. We're going back in time a little here, but this problem was the limit of f of x as x approaches 0, where f of x is x if it's rational, negative x if it's irrational. Well, if we were in an analysis class and we were doing delta epsilon proofs, we could go through the delta epsilon proof. But I'm more interested in like people recognizing this is pretty straightforward if you understand the idea of the limit. So one thing one might do, one might want to think about what the graph of this looks like. So if x is rational, it's just x equals f of x equals x, which is, you might draw it this way, kind of little dashes here. And then if x is irrational, it's this other line. Again, you can't, this is just representational. Both the rationals and the irrationals are what we call dense sets, which means that between any two, you can find another one. Between any two rationals, you can find a rational, and any two irrationals, you can find an irrational. So, if we were actually to, try and represent this more fairly, we'd have solid lines here. So the question asks for the limit as we get close to 0 from both sides. Well, if you remember, the idea behind a limit is there's some value we're going to get close to. Obviously the limit equals, obviously it's getting close to 0. That doesn't mean it has a limit. And in this case, you might be concerned about the fact that the function is jumping around very rapidly, infinitely rapidly. So what tells us that this is true is that, given, some distance from 0, we can always kind of bracket it. We can always put that delta around it. And if you remember, have some epsilon greater than 0. And we want to bracket it with a delta greater than 0. When we're using the distance from, from the limit, it's always in the absolute value. So we're always getting, the absolute value is always getting closer and closer. So, again, a simple answer of 0, well, that would be an answer to this problem. But it's, again, you might think does not exist. It's kind of trying to trick you a little. If this, instead of being x, was like 1 and negative 1, right? Well, then we have something more like this, where you have a bunch of values here and here, and then jumping back and forth when you get close to 0, they don't really get closer to anything else. So, I'm just wondering, are there any questions about that problem? It's not, at your level, it's not that important to have gotten this. And, it's just, since I gave the problem, I wanted to at least give you the opportunity to see that. Okay. All right. The next thing I wanted to talk about was the linear approximation. And before I do the hard problem, I just wanted to go over an easy one. Right? So in this example, we have 1.999, 3 nines. Gosh, I can't even read on this screen. Is it squared you want it to be? Well, maybe I can, no. Oh, 4. Okay. Ah. Oh, now I'm covering my screen, aren't I? I don't want to do that. This one's gonna turn this off. So we want to calculate this using a linear approximation. So the first thing to notice is that the function we're interested in is f of x equals x to the 4th. And we're going to need the derivative, which of course is 3x cubed. So what we want to do is we want to write this as 2.000 minus 0.001 to the 4th. So what does our linear approximation tell us about f of x plus h? Well, it's approximately equal to x to the 4th plus h times f prime of x, right? Which is h cubed. I have to tell you people, I'm not having a really good day here. I mean, cat died, I've got my notes at home, so bear with me while I, that's not a good excuse, but here we go. All right. So it's, h times f prime of x. where x is now 2, h is negative 0.001. Okay, so that's a lot easier to plug in. 2 to the 4th plus 0.001. F prime is 3 times 2 cubed. So we get 16 plus 0.001 times 8, 3 is 24. But times, divided by 1,000, so 1, 2, 3. Well, take a look at this. So 16.024. That's right. No, it's not.
Professor?
I guess let me try again. Oh, I forgot my h, right?
Professor?
Yes.
The derivative of x to the 4 is 4x cubed.
Thank you. All right, let's try again here. This is 8, 16. I still don't, oh. It's not 0.001, it's negative 0.001. So I have to subtract this, so I get 15.984, I think. No. I'm still not going to get it right. I'm going to rely on my friend's calculator here. So 32.001, and I subtract 16. Oh, 15.968. All right. All right, so that's, this is the easy problem. What fun. 1.999 to the 4th, 1.999 to the 4th is actually, according to my calculator, 15.96802,399, and something after this. So you can see the approximation is pretty good. All right, I wanted to go through that so that when we go through the hard problem, it's a little, we're not, kind of thrown off by the details. Okay, so the hard problem is cosine of 29 degrees. Well, okay, that's f of x is cosine of x. My derivative is negative sine of x. So f of x plus h is going to be approximately f of x plus h times f prime of x. All right. So looks like we want to write this as cosine of 30 degrees minus 1 degree. Well, why do we want to do that? Well, I'm just going to do the quickie trig thing here. I got a 30-degree angle. If my hypotenuse is 1, my leg is a half, the adjacent is square root of 3 over 2. And my cosine of 30 degrees is going to be square root of 3 over 2. So I just kind of run along And I say, all right, so cosine of 30 degrees plus negative 1 degree f prime, well, that's negative sine of 30 degrees. Sine of 30 degrees is a half. And, okay, so square root of 3 over 2, minus minus, that goes away, minus a half. All right. And let's just see what we come up with. I mean, it does seem a little absurd if I can use calculator for square root of 3 over 2, why not just figure it out? But there's a point here. Okay, square root of 3 divided by 2 minus 0.5 is 0.3660. And I think, well, as long as I've got the calculator, just put it into degree mode, okay. And let's find the cosine of 29 degrees. Oh, 0.874, well, that's enough. Something went wrong here. Anyone see what went wrong here? Which is the whole point of showing you this. Yes, Emily.
Sine 30 is a half. It's negative sine 30, and then it's negative degrees, so you would add half.
Okay. I'm slow today.
Got it.
Again, slowly. First part.
Sine 30 is 1 over 2, right? So it's negative sine 30, so it would be a negative 1 over 2, but since it's negative 1 degree, it will be
Oh, I got head. Oh, okay. All right. Let's try that. This could be a lesson in how not to do things. Plus 0.5. Oh, that's, no, that's 1.366. So that's not right either. Thank you for catching my mistake. But there's another really big mistake here. I'm wondering if anybody caught it. Okay. It's a little subtle. About 10 years ago, I was teaching a high school calculus class. It's great, because I only had like 5, well, it was a tiny school, and we had pre-calculus up in the same session, but there were only like 4 calc students. And I gave an exam, and this one student came back with all these weird answers. It would say, what's the derivative of the sine of x? And he would be like cosine of x times like pi over 180 or something like that. What? Where did he get this weird stuff from? Well, he was using a TI 89 calculator, which does derivatives for you in closed form. You know about that. Calculator that'll do it for you. But he had it in the wrong mode. He had it in degree mode. And the sine of x is only equal to the cosine of x when x is in radians. That's what our problem is here. This is not quite what we want. If we want the cosine, the derivative of the cosine to be the negative sine, and we're in degrees, we have to convert degrees first. So our equation should really be cosine of x over 180 times pi. Now, what happens when I find the derivative of the cosine of x over 180 times pi? It's not the negative sine of x, is it? We need the chain rule. So it becomes x over 180 times pi times pi over 180. So we have to insert this here. So it's 1 degree times negative 1 degree times negative sine of, well, it's going to be 30 degrees times pi over 180. Okay, let's see if that works out any better. So square root of 3, 2 plus 0.5 times pi divided by 180 is 0.8747525. Probably too many digits there. And the cosine of 29 degrees is 0.87461970. Oh, again, too many digits. But we can see that the error is in the fourth place. All right, so there's kind of two messages here. When you're dealing with trig functions, keep in mind that our derivatives only work in radians. And if you're using a calculator, always make sure you know what mode you're in. If you're in the wrong mode, you're going to get very funny numbers, very funny noises. All right, is there any questions on this? Everybody okay with this? All right. Okay. The next problem I want to go over is one I didn't really expect very many students to get anyway. But there was an example in the book, and we did talk about this a little. X cubed minus 15x plus c. And we want to show that on the interval -2, 2, that it has at most one solution. Show this using Rolle's theorem. Well, okay. I think I mentioned that, Rolle's theorem, it's not very useful for us at this level, but this is the kind of problem you throw at it. So how would we go about this? Well, what we want to do is a proof by contradiction. That is, we assume this is not true. That there's some f of A equals f of B. Wait a minute, I want to get this right. Which equals 0. And what does rules tell us if this is the case? If there's a C between A and B, such that the derivative at C equals 0. In other words, we have something, a situation like this, where we have an A and B, where our function is 0, and we know that there's some point here, some C, where the derivative is 0. I guess they could have worded it differently. This C and that C are not the same C. So let's call this D. All right, well, that's our assumption that this is true. Now we want to use that to try and find a contradiction. So clearly we need f prime of x, which is 3x squared minus 15. And we want to find a C equal to 0. Okay, we know how to do that. X squared equals 15. X squared equals 5. So x can equal plus or minus the square root of 5. Take a look at what that's actually equal to. It's equal to plus or minus 2.236. Okay, anyone see what the contradiction is? I found my C, right? Well, wait a minute. C is between A and B. A and B on the interval -2 to 2. I just have a number line. I have 2, -2. My A and B are here somewhere. C has to be out here, right? So there's no way C can be between A and B. That's our contradiction. So our assumption that there are two solutions is false. This again, not something I want to hold you responsible for unless you want to go on and become a math major. Oh, can someone like flip on the light switch over there? Thank you.
I have a question.
Yes.
So what does Rolle's theorem necessarily state?
Rolle's theorem states that.
Is it just that whole section in there?
Well, there's more to it. Okay. Rolle's theorem, you need a function which is continuous, right? All polynomials are continuous, so we satisfy that. I didn't, that would be a more detailed evaluation. It says that if you have a function, continuous function, where f of A equals f of B, actually it just has to equal some constant, that there exists some C, where C is between A and B, such that the derivative of C is 0, right? That is, we have some function where a and b are, f of a and b are equal. It's smooth, so between a and b, the derivative has to go to 0 at some point. That's in contrast to the mean value theorem, which says you have 2 points and a continuous function going through them. Well, you have a line connecting them which has some slope, right? It says that the derivative, this is f of x, the derivative of x has to equal m at some point here, right? It's a little more complicated. Again, there's not much you can do with these in this class. These little tricky proofs, which I don't think are, necessary for your understanding of calculus at this level. But they're really useful theorems when you go beyond this. They show up all the time where you're doing some complicated proof, and then all of a sudden, they just throw in the value theorem, therefore, blah, blah, blah. It's true. Okay. This is kind of the abstract entertainment for today. The last problem I want to go over is not abstract at all. It's very straightforward. It's just hard. It's hard to do all the work to get it right. This was I'm sorry. No, that one. The problem I'm thinking of is not yet. This next problem, I don't know, it's not that hard. It's just, all right. I'm gonna write it up first. So we have f of x equals x to the 4th minus 2x squared plus 3. And I'm going to let everybody help me with this. First thing we want to do is find where it's increasing and decreasing. So how do I do that?
Find the first derivative.
We certainly want to find the first derivative. Okay. What's the first derivative going to tell me?
Critical points? Critical point?
Certainly, we're going to need to do that. So this is x squared minus 1 times x, or x minus 1 times, I'll write it this way, x times x plus 1. So we have critical points at 1, 0, and negative 1. But in trying to answer this, what is the first derivative going to tell us about a region of the function? This is in the homework, this is in the lecture, this is pretty basic. I know you know the answer. I want to sit on it for a minute. I have some function. It's increasing. What do I know about its derivative? I know about the derivative if it's increasing. You can just kind of look at it and think about it. It's hard to get excited about this. All right. I'm gonna let Beth Ann go first here,
Is
yes.
it when it's greater than 0?
Yeah, derivative is positive. When it's decreasing, you know, it's negative. When it's 0, it's horizontal, right? So it's not increasing or decreasing. Okay, so what is knowing these critical points going to tell me? Well, between the critical points, it's going to be either positive or negative. It has to go through 0 to change. So we could just check a point, like we could check at 2. That's, to the left of 1. We could check like 0.5, that would be between 1 and 0. Or we could check like -2 or +2 to see what it's like out there, or I missed something? Yeah. -0.5 and +0.5. Right, so these are the 4 regions where the derivative will have different values, either positive or negative. Now, as it turns out, since we don't have any duplicate critical points, we don't have any, x squared here, so 2 roots, it's going to just change, in an expected manner. We'll try that and we'll take a look. All right, so -2 would be 4 times -2 to the 3rd minus 4 times -2. Well, I don't really have to figure this out. 2 to the -3. -2 to the 3rd is negative. I guess I do probably have 8 times 4 is -32. This is going to be an add here, 8. So it's negative. So out here, it's going to be decreasing. From negative infinity to -2. Just to see that I'm not making this up, let me put in -0.5. We'll see that that's positive. So for -0.5 cubed minus 4 -0.5. So this is 4 over -4/8 plus 4/2. So clearly that's going to be positive. So from -2 to 0, it's going to be increasing, positive derivative increasing. And likewise from 0 to 2, it's going to be decreasing.
Would it be to 1 and -1, since those are...
Did I say, I'm sorry.
No problem. I
Yes,
was just-
thank you.
Okay.
Absolutely correct. Thank you. Okay, so that's A, find the increasing and decreasing regions. Part B, find the local max and min. How do we do that? I think we already have. How do you find, on a continuous function, how do you find the max, local max and mins? Yes?
You see where the derivative is changing from decreasing to, or the function is changing from decreasing to increasing?
Okay, you're answering my next question. You're assuming the first, which is good, right? You find where the zeros are, right? And now, you're quite correct. If it's going from decreasing to increasing, at -1 there'll be a min. And if it's going from increasing to decreasing, there's going to be a max. And likewise here, the opposite is going to be a mid. Okay, good, thank you. Last part, this question was find the intervals of concavity and the inflection points. Intervals of concavity and points of inflection. Okay, let's do the second part first. How do I find the points of inflection? Yes?
Second derivative. Second derivative.
Second derivative. Okay. Take a little room here. So that's 12x squared minus 4. Okay, what do I do with that? What do I do with the second derivative to find the points of concavity?
Set it equal to 0.
Set it equal to 0. It's 12x squared equals 4. X squared equals 1/3. X equals plus or minus square root of 1/3. Okay, so those are the points of inflection. We want to know, between these points, we have three intervals. So we want to know what's going on there. Is it concave up or concave down? How are we going to figure that out? Well, again, you can do this intuitively, right? It goes from decreasing to increasing, right? Is that right? Am I doing that wrong? I think I'm doing that wrong. Doing that wrong. No, that's not right. How about this? We decided it's got a min, -1, max at 0, min at 1. What's going on here? Square. Square root of 1/3, that's between here and here, right? Negative, and then the positive is over here. So on the first interval, it's going to be concave up, it's going to be concave down, and it's going to be concave up again. All right, I want to haul in our friend Desmos here, so we can actually see what this actually looks like. X to the 4th minus 2x squared. Plus 3. Okay, so that's kind of what we talked about, right? It's got a minimum here at 1, a maximum at 0, a minimum at -1, maximum at 0, minimum at 1. It's got a point of concavity in here somewhere, and over here, the square root of 1, negative square root of 1/3, and square root of 1/3. So, yeah, kind of all fits together. this was like probably the hardest of those examples. We had homework problems, so probably we should go over that one. All right. Last of the hard problems, as I was saying before, it's not conceptually that hard. It's just, there's a lot of work involved. Wait a minute. Sorry. I keep forgetting all this fun stuff we might have done. I'm gonna skip one. Do the one that's just a lot of work. And remember this one? Limit x approaches infinity. 2x minus 3 over 2x plus 5 raised to 2x plus 1. Anyone get this? Think they got it? Remember it? I don't think you forget it if you do this. All right. Does anyone recall how we solve these problems using L'Hopital's rule when we've got an exponent? Like we have like the limit x approaches 0 or x to the x. Do you recall what we do? Uh-oh, I guess I didn't assign enough homework. Well, for something like this, instead of trying to find what y is as x approaches 0, you look at the log of y. As x approaches, well, x log x. And then we have to rewrite this in a way that L'Hopital's rule will work. So as we get to 0, the log goes to, you want to recall what the log goes to as we go to 0? Negative infinity. And this goes to 1 over 0 goes to infinity. So it'll work. So we find the derivative of x, 1 over x squared, negative x. Well, the limit as x goes to 0 of negative x is 0. That's just the log of what we're trying to find. So e to the log of y is y. E to the 0 is 1. So that's how you would solve these, but this problem adds just a lot of additional pain and suffering. I found when I did it, I get an answer, but I don't know where the answer comes from. So I thought, well, let's make it a little more general. Call this 2x minus a, 2x plus b, and 2x plus c. I mean, I could put in 3 and 5 here and follow it along, and I'll get a value, but you can't, like, where did that come from? Okay, so that's my y. So my log of y is going to be 2x plus c times the log of 2x minus a over 2x plus b. And again, I have to put this in a form that I can apply L'Hopital's rule. So if I write this as log of 2x minus a, 2x plus b over 1 over 2x plus c. Well, let's check now. As x goes to infinity, 2x goes to infinity. 1 over 2x is going to go to 0. This is going to over 0. Here we have 2x minus a over 2x plus b. As x goes into infinity, this is going to 1. But the log of 1 is 0. So we have an indeterminate form. So we can apply L'Hopital's rule. All right, here's where it gets a little tricky. We have to find the derivative of this. All right, let's give it a whirl. The log of 2x minus a over 2x plus b is 1 over this. So it's just a reciprocal. 2x plus b over 2x minus a. Then I have to find the derivative of what's inside the function using the chain rule. Oh goodness, I have to use my quotient rule. So that's going to be derivative of f, which is 2 times 2x plus b, minus the derivative of g, which is 2 times f, 2x minus a, all over g squared. Oh boy. And that's just what's on top. On the bottom, I have 1 over 2x plus c. Well, that's going to be negative 1 over 2x plus c squared. Again, using the chain rule minus 2. Question?
I think we're confused if it should be 2x minus a squared instead of 2x plus b squared, because that's, where is it?
Okay,
I feel like
so
that's
the
all-
log, derivative of the
Oh.
log of x is 1 over, let me, the derivative of the log of some function is 1 over the function times the derivative. That's the chain rule at work.
Right,
So,
but
yes.
isn't, you're using the quotient rule? And is it
Well, I'm,
bottom function, or is it,
okay, so I'm going to use the quotient rule for this.
yeah,
So I have to find the derivative of this. So it's the derivative of f, which is 2, times this, minus the derivative of, I forgot which one, times this. And then g is, this is the g squared. Let me write that out. Derivative of f over g.
oh, okay, I see.
Oh, that's good.
Yeah, I was just confused on what was G and what was F.
Yeah, okay, yeah, it's a lot of work. You gotta follow it carefully. No, all right. So, okay, I have a 2 on the bottom and a 2 on the top, so I can get rid of that. I've got a 2x plus b here and 2 of them here. Simplifies. 2x plus b minus 2x minus a is b plus a. So let's see, I've got b plus a on top. We've got 2x minus a on the bottom from here. We have 2x plus b from here. And then this flips over. We've got a minus from there. 2x plus c squared. Okay. So what we were trying to do is find the limit as x goes to infinity. Now, I can do this a little better, but I'm going to hand wave here. 2x plus c over 2x minus a. Well, as x gets very large, the c and the a become insignificant. It goes to 1. Got another 2x plus c over 2x plus b. Same thing, it goes to 1. So this goes to negative b plus a. Well, now would be a good time to... Oh, I did something wrong there. Oh. That's right, my a is 3, my b is 5. So this just becomes negative 8. Remember, that's the log. So if the log of y is negative 8, y is equal to e to the minus 8. And you can see where the 8 comes from. It's this a plus b that we started with all the way over here, 3 and 5. What I found particularly concerning about this problem, like most of the problems, if you just graph it, you can kind of see what's going on. If you try and graph this, well, first of all, whatever is happening, it's happening way over here at infinity. And it's such a small number, you're not going to be able to tell whether you got it right or not. So the usual way of like checking doesn't work. All right. I guess time for a break. We'll be back in a few minutes. We're going to do something different when we come back. We're not going to do problems. Just the time for a scan call, too. Hello. Please, when you grow up and get a job, do not get a job in a call center calling people up and trying to scam them, please. Grow up and be good citizens. So, not everyone was here at the beginning of class. I'm going to repeat myself and come up with a solution to the calculator problem on exams, because I have a few of these calculators myself. I'm going to get a few more. So, during future exams, the midterm and the final, if you don't have such a calculator and you wish to use one, you'll be able to borrow one. Now, there may not be enough for everybody, so we'll just switch off. I don't think you're going to need a calculator that much that it's going to slow you down any. Today we're going to look at these. Is there anyone who has not used a TI calculator before? One of these graphing calculators? Okay, all right. So you will pay especially close attention. I have 3, and I want to divide up these 2. It's okay if people either have a computer emulator, or have one of these. In the back row, who does not have a calculator? Okay. How about Kevin's row? Who doesn't have a calculator? Okay. Please return these at the end of the class. Can you pass that back?
Oh no, I have a computer. I can use that.
Oh, you can use your computer?
Yeah.
You have an emulator?
Yeah.
Okay, all right. Wow. So everybody, okay, all right. You won't be able to use a computer or a mobile phone version during the exam. But as I said, I will have some of these. I also, if you happen to have a Windows machine, I have a program to provide you with which emulates TI-83, which I was hoping to use in this class, but I can't because we only have a Mac. So I can actually bring up a picture in my notes. Okay. Coming on. No, it's not. Okay, so for all I know, you're all experts. I can't assume that. I'm just going to go over some of the basics here. You know, you have a screen, and you have a lot of keys. And to make matters worse, there are two shift keys. Second, which is, you know, you're going to look at the gold values, or the alpha key, which is going to be the blue value, which we're not going to use that much. These things have just a huge amount of functionality. Stats course, or calculus, or any, you know, pre-calc has a lot of stuff. And we're going to try and focus on things I think that would be most useful for the class. Least of all, you can hit the shift key and adjust the contrast on the screen or the brightness. That's not that important. Up here, you have some menu keys. In particular, what we're looking at here is the y equal key. And here we have a list of functions we can enter. Quite honestly, I put in more than one equation once or twice. I put in two equations, but I don't really know that well how to manipulate them. There's kind of a switch that turns them on and off if you want to graph more than one together. If you want to put two equations up and find their intersection, you'll have to do that, but I've never really needed that. There are some things you should know about this entering a function. First thing is the different models work a little differently. The lower end models, when you say, when you use the little hat meaning exponent, this is x cubed, you get this. In the more advanced models, it's actually going to shift up, give you a superscript. And the thing you have to be careful about when you do that is if you're typing in an equation and you want to get out of the exponent, you have to press the cursor key. You know. In other words, if I just typed in x exponent 3 minus 5, the 3 minus 5 is going to be in the exponent. So there's something to be aware of. I think like 84 or anything higher than that. Okay. The other thing is the x here they're referring to is this key over here. This key says x t theta, and I don't really know what that last item n. This is like a lot of things on the calculator. This is mode dependent, right? For just a regular graph, it's going to be x. If you're doing a polar graph, if you're going to use theta, t, I know you use if you're using parametric equations, which we're not going to really go into that. But again, it's this x, not this letter x down here, and that's your variable. I guess I should also say there's I don't actually know how this thing works. I know if you put the cursor up there, you turn a flag off and on, but it's not something I do very often. Okay, so let me see if I have any more good pictures here. Oh, well, yeah, I guess this is worth saying something about. Gosh, I don't even know. This is okay. If you hit the second format key, you'll get this screen. And this gives you the ability to adjust your graph, whether it's polar or XY graph. You can turn the axes off. You can kind of adjust the way it looks. Best thing to do with something like this is experiment a little with it. All right, so here now, and unfortunately I can't demonstrate live, but you've got a calculator, so you can try these things out. To get from any of these menus to get back, you want to hit second quit, right? Also, if you hit the mode key, which is useful, you want to check whether you're in degree mode or radian, or using trig functions. You can again get back second quit. These two buttons, window and zoom, allow you to adjust the scale in different ways. Window gives you exact control. You can enter the numbers. And zoom lets you, just kind of jump in and out or pick a predefined set of scales. And then typically you're gonna hit the graph button, and you're gonna see in the upper right-hand corner while it's working, you're gonna see a little line here that's flickering, and it'll draw your graph. Why doesn't everybody just try this? Just plug in x cubed minus 5x squared plus 2x, and see if you can get a graph. Know how to do something, or you get into a funny spot, look at the person next to you and ask for help. Have to ask, does this have the same Yeah, it's the same functionality. Oh, it's on your cell phone, of course. That's why it's so small. Yeah. All right, so you should see something kind of like this. And again, if you hit like the zoom, and I guess zoom out is 3, then you hit enter, it's going to redraw it. With the scale adjusted. All right, is everyone okay with that, or is anyone having any trouble getting a graph, basic graph? Okay. Other things that I find useful, and you just have to, you have to experiment with them a little. There's the shift calc option, which gives you a number of options. One is value. For value, you just type in a number, and he's going to plug that into the equation, into the function, and give you the value. So if you have some function and you're trying to get points out of it, it's a useful feature. You pick 2, 0. Okay, this is useful for. I just want to back off and say something general about calculators, computers. We're not doing calculus on these. We're doing kind of numerical stuff, which means that we get values that are not always exact. And in some painful situations where we've kind of overcome the limitations, where we've gone beyond the limitations of the computer involved, we're just going to get completely inaccurate, bogus values. Now, I'm not going to try and fool you by creating a situation like that, but you should be aware of it. I don't know, it's probably like 32-bit or 64-bit, numbers in here which have some limitations. Okay, for the 0 function, these cursor keys are going to come in because he's going to ask you for where to start looking for a 0. So if you have some kind of function that is like this, if you're going to find one of these zeros, you have to kind of tell it where to start looking. And if you have multiple zeros, you might have to do this multiple times. And it'll go ahead and calculate to whatever degree of accuracy you found your 0. Solving the equation f of x equals 0. Same thing with minimum and max. You give it a starting point, and he looks for where the graph goes from positive to negative, negative to positive in slope. So number 5 is the intersection. Again, I plead innocence, ignorance. I'm sure you have to have two functions, and then you have to plan where to start, where to look, and find where they connect. If you ever have two functions, I'll tell you how I get around this. If you ever have two functions in g of x, and you want to find their intersection, instead you can do this. You can just put in the function f of x minus g of x, and look for where that's 0. Look for the 0. It's a way around my ignorance. And it's 5 is the intersection. And 6, it's actually going to give you, I'm going to try and calculate using have a numerical limit, the derivative at a certain point. I have never found a use for that. I can always evaluate the derivative of the function and just plug in the value. But there might be circumstances where that's useful. And the last item on the list is integration, numerical integration. We're going to cover that later in the class. So at that point, maybe we'll come back and we'll look at that function. Okay. I think that's most of what I wanted to go over. You're not going to be good at this without playing with it a little. So you might want to apply it, go back and find some homework example and just apply it, if they give you some function, look at the graph, try some of these functions. If it's going to be useful for you, it's going to be useful because you play around with it a little and learn how to do it. Now, if you already have, I'm sorry, I bored you or wasted your time. If you would like some additional help with this, please come to my office hours and we'll work on these. I think that's probably all I have for today. We're kind of early, so I did plan a little more dynamic version of this, but all right. I'll hang out here for a little while if anyone wants to come ask questions about this. Bring back my calculator. If for some odd reason you don't have one, you want to borrow one, that would be okay too. Let me know. Or if you would like the program, the Windows emulator, let me know that. And I can send that to you.
Oh, we got 1:30, that means I need to get everybody. I don't know.
Are you gonna take the bus? Oh, are you gonna stay here and then go, or?
You guys want to get lunch with me?
Yeah.
Oh, wait, look like
Uh-huh.
Wait. Go there straight from here, or like go home and then go there? Where are you going? Where?
Let me come over here.
I am wondering, like, how many work assignments
3
I'm
minus
missing?
2x.
'Cause, like,
But
it's been a
after
while
I
since I did math.
There's
do
one
the
of these.
derivative of that, it's not
So not that much.
I'm probably
That's not how
missing
you
like
find
three.
it.
Yeah, that's not bad.
Okay.
It's pretty bad.
Like a lot.
I only did like one
Understandable.
homework after the test.
Boy,
Okay, that sounds like more than 3.
well,
No, it's been like 2 weeks.
I forgot what the question is asking,
Well,
but I just do it.
they want the critical point, they'll say.
Who's that?
So,
Really?
3 minus 2x. Okay. That's actually the same as 2x minus 3.
Mhm.
Yeah.
Oh my, that's the wrong way.
So,
They're actually keeping that on.
critical points, if you have like a polynomial or a smooth function, right? Critical points are where the derivative is 0.
Yeah, so it could be like maximum or critical.
Could be a max or min, that's a different question, right? For something like this, 2x or 2x minus 3, okay, so minus 3, okay, it's going to look like this. The derivative from here to here is just 2, and the derivative here is negative 2. But the derivative here is not defined. So okay, derivative where the derivative doesn't exist is a critical point, right? So with an absolute value, the place where that happens is where it's equal to 0. So we get 2x equals 3 or x equals 3/2.
Oh, I see.
It's not there. So that's where it could have a local minimum. Well, actually, I did this wrong. All right, x equals 3/2 is going to be 0. Right. Because it's always positive, because it's just all within this absolute value.
Alright, next question.
This actually is what I was thinking. I was thinking of the intercept is -2 or +2, or 3 or +3. Okay.
So next one is finding the critical point of this one. So it's p minus 1 over p squared.
P squared
Yeah, and then plus 4.
plus 4.
Yeah.
Oh.
So we'll find the derivative of that first. So let's use the quotient rule.
Well, before we do that, let's just notice that this is never 0. So this will have a derivative everywhere, right? So, yes, I don't remember this one, but you would need to use the quotient rule. So the derivative of p minus, right, so f prime g minus p prime f over g squared. So f prime is just 1 minus g prime is 2p times p minus 1 over p squared plus 4 squared. So we don't have to worry about the denominator being 0. Right? It can't be. So we just have to set this equal to 0. So what is this? P squared plus 4 minus 4p squared plus 2p equals 0. So -3p squared plus 2p plus 4 equals 0. And we can find where p is equal to 0 using the quadratic formula. So let's try that. -b plus or minus the square root of 4 plus 4 times 4 is 16 times 3 is 48. This doesn't sound right. Something sounds fishy here, but all right, all over 2a, which is -6. Well, I think I made a mistake here. Can I look at that the problem again? P minus 1, p squared plus 4. Check my work. I don't remember getting this one. That's okay, it doesn't
It's on
matter.
the next one.
It's, even if you made up the problem, it's a good problem. So 2p times p minus 1. So we have p squared plus 4 minus 4p squared plus 2p. That looks good. P squared minus 4p equals 3. That looks good. So -2 plus or minus the square root of 52 -6, or 2 plus or minus the square root of 52 +6. Divide this by 2, this by 4, this by 2. So that's where this is equal to 0. why don't we, you know, this doesn't feel right? This is a perfect opportunity. Right? So let's put this in. So you have to use x. To think ahead and put parentheses x minus 1 divided by x squared plus 4. Let's look at that. I think I want to just already messed up my scale here. So blue box is a good place to start. I hate when this happens. This is, we could just do a thing on this standard.
Wait, how much was the graph? Like the original?
This one's kind of graph.
Oh,
Yeah, yeah. Okay, so let's zoom in. See if we can learn. X minus 1 over x squared plus 4 cares.
let me go.
Okay, so let's try window. See, minus 5 plus 5 minus 5 plus 5. Ooh, that's starting to look interesting. So it seems like we want to zoom in on the x part of the scale here. We don't want to squeeze it any more this way. So with window, I can adjust the y.
So like 1 maybe.
Minus 1 to 1. And actually, it probably, ooh, now we're starting to, you know, this takes a little, you know, messing around with it, we'll say. I want to make it a little wider. Minus 7 plus 7. I mean, it's not a square graph now, but okay. So it looks like it has a 0 at 1. That's not a surprise. It looks like it has a minimum here.
Before we do that, I just want to make sure.
Yeah.
So like for example, I just want to make sure like the way I'm finding the critical point is correct. So for example, if like assume that if a function is like that, then how you find critical point? You just find it through the
Set it equals a 0. Yeah.
And then the way I do it is like I factorize it.
Mm-hmm.
And then from here you can just tell it's like 0, like 4.
Yes, that's exactly right.
I just want to double check I'm doing the right thing.
Okay, so this one, we can, all right, let's actually use the feature here. First, let's find, let's say, 1 plus square root of, let's see if we get that, divided by 3. So it's like 1.53. 1.53. And 1 minus square root of 13 divided by 3 is negative 0.868. Okay, so now let's go to Calc 0. All right, no, that's not what I wanted to do. Calc minimum. So now at this point, you see we have this little star here, and see it says left bound.
So I have to move it like all the way to the
Just a little beyond where we think it goes. And the right bound, move a little to the other side. And now we tell it, we guess, I don't know. You're going to have to type in a number too. So now it's busy working, and he comes up with, negative 1.236, which suggests I've done something wrong. All right, let's first check x minus 1 x plus 1. The derivative is f prime times p squared plus 4. It's 2p minus 1. P squared plus 4. Oh! I can't multiply anymore. It's not 4, it's 2. Okay.
I don't quite get this one, so how did you went from this to that?
P squared plus 4, that's 1.
Oh, so just expanded.
Minus 2p squared minus plus 2p.
Oh, so you don't have to do anything.
Well, we're going to set this equal to 0, but
Oh,
we can multiply this out.
Oh, I see.
See, because this is always greater. If it ever were 0, then we have to, like, if it was like this, then we can't do it. we have to be a little more careful because at 2 and negative 2, this goes to 0 and then it blows up. But we're not worried about it. So negative p squared plus 2p plus 4, or p squared minus 2p minus 4. Okay. So 2 plus or minus the square root of 4 plus 16 over 2. So 1 plus or minus the square root of 10. Wait. 20 divided by 4, 5. Okay, so let's check. 1 minus square root of 5 is
1.23. Yeah,
negative 1.236.
which is
Exactly what we got.
Oh, I see. Yeah, so
Now we didn't find the max. We could do that too.
now I know what's the problem. I have to
Okay.
use the rules. Can I take a picture?
Oh yeah. It's kind of messy.
Alright, I think I know how to do this one.
Okay.
Alright, so next question.
You just have to be careful that when you multiply 2 times 1, you don't get 4.
This one's probably the same, right? I have to use the quadratic, which you should solve it. X squared plus 2 over.
You just have to be careful because at a half, you also have a critical point. Is that right?
Yeah.
Yeah, because the derivative doesn't exist there,
Mhm.
right?
Wait, so
Yeah.
for this one,
Mm-hmm.
there should be like another critical point over here, right? Like other than this one.
It has nothing to do with this. It just has to do with this has one. This is wrong, right? We decided it's 1 plus square root of 5. Oh, I have to turn it on. 1 plus square root of 5. Plus square root of 5 is 3.236. So now, we look here, right? This looks like a maximum over there. So let's find the maximum. Yeah, we could start there. And then we want to go over the bump. Okay, there. I want to guess that. I want to guess something over here. Okay, let's see, it's it's working. Okay, so what do we get? 3.236.
Oh, I see.
It's very satisfying.
So like, sometimes I don't even have to do this. I can just find the, because like critical point is sometimes it's like just the minimum and the maximum of your ask.
Yes.
So oh yeah, so like I can always like double check my answer with the calculator after I solve this.
This is, yes. It works best if you have a polynomial. You know. Yeah. You know, where they're nice and smooth, you know how many zeros they can have, right? They can have up to n zeros. It has n zeros, but they can be complex numbers, so you may have none. Like if you had x to the fourth plus 4, right? It has no zeros. But the derivative, this will have a 0, 0. So it's going to go through 0. All right. Now that's not going to be a min or a max, but it will be a point of inflection. Right? So, you know, whenever you have something like this, you know,